This is the final presentation for graduate algorithms. My name is Dania Elmadhun, and I will be presenting along with Andrew Guttman. And today we're going to be talking about algorithms for solving SAT problems, conflict-driven clause learning algorithms. So to start, we want to take a brief look into NP-complete and what it means. It's saying that we have yet to discover a polynomial time algorithm to solve problems in NP. Now, P versus NP is one of the most famous open problems in computer science. P problems are solved using a deterministic Turing machine in polynomial time, which basically means that they're easy to solve and easy to verify. An example of which is the greatest common divisor. But what's a Turing machine? A Turing machine is a very simple model for computation that is an infinitely long tape broken up into cells that contain zeros, ones, or blanks. The head of the machine hovers over each cell with the ability to read and write into the cell, and then moves left or right of each cell per time step. It seems pretty simple, but all modern programming languages boil down to a version of the Turing machine. Now back to P versus NP. NP problems have a solution, or certificate, that is easy to check in polynomial time, but not so easy to come up with the solution in the first place. For example, if given a Sudoku puzzle, coming up with a solution would mean running through all possibilities, which takes a really long time. Problems in NP-complete are in NP, but also considered NP-hard, where they are at least as hard as any other problem in NP. Now this is a hot topic because P versus NP is bound by NP-complete problems. If we can solve any one problem in NP in polynomial time, then that means that we have just figured out if P is equal to NP, since all problems in NP-complete can be reduced to each other. So if one problem can be solved in polynomial time, then all problems in NP can be solved in polynomial time. So what's the SAT problem? SAT is like the king of NP, as it is able to completely represent every other problem in NP. It's more formally known as the Boolean satisfiability problem, and it was the first problem to be proved to be NP-complete by the Cook-Levin theorem. They consist of Boolean operations, and, or, and not, variables like x1, x2, and x3, and parentheses. For the examples provided, an assignment of true or false is given to each of the variables. The first example is satisfiable with the given solution, however the second is not. Proving SAT is NP-complete basically led a domino effect of other problems being proved to be NP-complete by reducing SAT to those problems, or taking a known problem and reducing it to the unknown to prove NP-completeness. We prove that satisfiability problems is NP-hard by proving circuit SAT, an analog of SAT, by using reduction. Before we get into the proof, we're going to define the three types of gates used in the circuit: the NOT, and OR gate that fit together to create a larger complex circuits, where we need to find the setting of variables that causes the circuit to output a 1 or a true. There are two parts to proving that the SAT problem is NP-complete, and we will be using circuit SAT, a flavor of SAT, to prove it. First is to prove that the problem is an NP, which asks, is there a certificate that can be checked in polynomial time? Or in other words, a solution to a given SAT problem that can be verified to be true in polynomial time. The second is to prove that the problem is NP-hard, or at least as hard as any other problem in NP, and any problem in NP is reducible to SAT in polynomial time. The proof is as follows, that any NP problem reduces to SAT by showing that any problem reduces to circuit SAT, which in turn reduces to SAT, originally proved to be NP-complete by Stephen Cook of the Cook-Levin theorem. There exists a verifier that runs in polynomial time which is encoded as a circuit. There is a finite number of gates, each with a sequence of outputs, an input assignment that can be verified by running through the values of the circuit, and a final output is achieved in polynomial time. Thus, circuit SAT is NP. Proof of NP-hard means it has to be at least as difficult as every problem in NP, where the circuit has a polynomial number of elements and is constructed in polynomial time, where every NP problem must reduce to circuit SAT. The simple but big idea here is that programs are basically circuits. Therefore, the key idea for the reduction is using a Turing machine as the code for the certifier as a circuit. Reduction of an arbitrary problem y in NP to circuit SAT so that every node or gate of problem y will have a corresponding variable in our circuit. The output of problem y is satisfiable if and only if the circuit is. The reduction runs in polynomial time to circuit SAT, and thus circuit SAT is NP-hard. I'm going to pass it over to you, Andrew. Thank you so much.
Thanks, Dania. Now that we've covered what the SAT problem is and why it's important to computer science through NP-completeness, we want to cover how SAT problems are actually solved. Now, the first most obvious way to tackle this is through enumeration, where every possible assignment of the variables are generated until one is found that satisfies the formula. Since there are n variables and each can hold one of two values, true or false, clearly this takes of order 2 to the power of n time. Another intuitive way to attack this problem is through guess and backtrack. Here we're also generating an assignment of variables through guessing, but instead of generating the entire assignment at once, we do a single variable at a time. If our guess for that variable does not create an unsatisfiable clause, then we move on to the next variable and guess for it. If that assignment does create an unsatisfiable clause, we backtrack and reverse the assignment and continue as normal. We do this until we find an assignment that satisfies all the clauses, or we've tried every single guess that we can, and none of them satisfy. Here we see an example of naive guess and backtrack being run over a Boolean formula, and we eventually find a satisfying assignment, not A, not B, C. In doing this, we notice that we have certain savings over enumeration, where some unsatisfying assignments are never generated, but we also notice a lot of wasted effort. For example, clause 3 enforces that B be set to false if we have a hope of satisfying the formula. Yet we still spend 2 guesses setting B to true. We also have an entire branch where A is set to true, but A never appears as asserting in the formula, so this branch makes no contribution to satisfying any clause. So, noticing this waste, it's natural to ask, can't we do better? Well, SAT is NP complete as discussed earlier, and we can't avoid that, but we can deal with some of the things we noticed in the last slide. For example, a unit clause where only a single variable appears, or a pure literal where a variable only has one polarity across all clauses lead to easy assignment decisions. We also observe that the order we make our guesses in matters. If we just happen to guess a correct assignment the first time every time, it would seem like SAT solving is not that difficult. It only takes constant time. Now there's no way to be that lucky, but we do want to find some way of avoiding too many bad or unproductive guesses. This all leads us to what is used in modern SAT solving programs like C3, conflict-driven clause learning. So, what is conflict-driven clause learning, or CDCL? Well, it's a search algorithm for solving SAT problems, specifically SAT problems presented in conjunctive normal form. CDCL provides a set of heuristics that guide its search, hopefully making it more likely to find a satisfying assignment quickly. CDCL takes many of its ideas from an earlier development, the Davis-Putman-Leitman-Loveland algorithm, and adds to it 2 key features, clause learning and non-chronological backtracking. Before diving in on CDCL, we need to examine this DPLL algorithm. DPLL does exactly what we discussed in eliminating easy waste. It applies a unit clause rule. Any clause where all but one variable is set to false, the remaining variable must be set to true. This can be seen in our simple examples where we have a clause of just not B or a clause of A or C when C is set to false. DPLL also does pure literal elimination, where any variable that only appears with a single polarity is given an assignment to satisfy it. So here, not A never appears, so we set A to true. Applying these rules can lead to cascade effects, where the rules can be reapplied, fixing the assignments for even more variables. The rules also need to be reapplied every time a new guess is made. Otherwise, DPLL proceeds as guess and backtrack did. Here is the same Boolean formula we ran guess and backtrack on. When applying the unit clause rule on clause 3 to set B to false, we notice we can propagate the rule immediately finding assignments for A and C. Something similar happens for pure literal elimination. So in this case, DPLL was a marked improvement over a naive strategy. It found a satisfying assignment without having to make a single guess. Here we run DPLL over a larger formula. It takes some guessing, but by applying and propagating its rules, it is able to find applied assignments earlier than guess and backtrack would, allowing it to notice and backtrack from conflicts earlier, such as when the assignment not A, not B, not C creates the implication that D must be true and that D must be false. It is also able to find that the assignment A, B creates a cascade, implying C and D must also be true. With this creating no conflicts, it is a satisfying assignment. Now, before we build off of DPLL, we want to know for sure that DPLL is correct. We accept that guess and backtrack is correct intuitively, so all we need to do is prove that the 2 additions of DPLL don't screw things up. First, the unit clause rule. Assume that there exists a satisfying assignment where a unit clause variable is set to false, but every other variable in the unit clause is already false. Setting the unit clause variable to false guarantees that that clause is not satisfied. Therefore, this cannot be a satisfying assignment. We've produced a contradiction, therefore we've proven the opposite of our assumption. The unit clause variable must be true. For pure literal elimination, assume that there exists a satisfying assignment where a pure literal is set to false. Since the negation of the pure literal never appears, setting the pure literal to true has no ability to disrupt this assignment and make it non-satisfying. Therefore, there is no harm in assuming pure literals to be true. Conflict-driven clause learning behaves much like DPLL. We start by applying and propagating the same rules from DPLL until we need to make a guess. When we make an arbitrary guess, we increment a guess level by 1, and then continue to apply our rules until another guess is needed or we reach a conflict. When a conflict is reached, we check the guess level. If it happens to be at level 0, this means we found a conflict before making any guesses, so the problem is unsatisfiable. Else, we analyze the conflict, using resolution to create a new clause that is added to the formula. We then backtrack to a previous guess level, invalidating all the assignments made after that guess level, and start applying the rules until another guess or conflict, continuing until all variables are assigned. We'll break down each of these steps in more detail. First, resolution. Resolution combines two clauses from our formula to create a new clause that is equally satisfiable. For example, not A or B or C and A or C or D can be resolved into B or C or D. We do this resolution by pivoting on A and not A that appear in the two original clauses. Resolution is only really useful when we have exactly one such pivot in our two clauses. SAT problems can actually be solved entirely by repeated applications of resolution. Since the new clause is equally satisfiable as the two originals, those two can be thrown away and replaced with a clause that contains one less variable. Doing this enough times will lead to either a trivially satisfiable or unsatisfiable clause that represents the full original problem. When CDCL runs out of applied assignments, it must guess. Every time it makes a guess, the guess level is increased by 1 and the assignment that was chosen is recorded as a guess. Applied assignments have an equal level to the highest level used in their implication. For the following example, not A is at guess level 1, not B at level 2, and not C at 3. The implied conflicting assignments of D and not D are at guess level 3 because they rely on the assignment of not C, which happened at level 3. The key feature of CDCL is clause learning. When a conflict is reached, the clauses that were used to find the implying conflicting assignments are resolved upon to create a new clause that is added to the formula. It is in this sense that the algorithm is conflict-driven and clauses are learned. Here, two clauses, 2 and 3, lead to a conflicting assignment, so the resolution of those two is the new conflict-learn clause. Note, if there are more than two clauses contributing to a conflict, we must continue to resolve upon those clauses until the learn clause includes exactly one variable that has been assigned at the current level. Here, the learn clause A or C has exactly one variable, C, that is assigned at the current guess level of 3. DPLL and the naive algorithm only undid the most recent choice when a conflict was found. This backtracking to the most recent choice is said to be chronological. CDCL instead backtracks to a point based on a guess level in the new clause generated on a conflict. Since this is not necessarily the most recent choice, CDCL is said to have non-chronological backtracking. Specifically, if the learn clause is a unit clause, we backtrack to level 0. This is because a unit clause enforces an unambiguous assignment before any decision needs to be made. Else, we backtrack to the highest level of assigned variables in the clause, excluding the current level that the conflict occurred on. For example, if the clause A or B or C is learned, with A being guessed at level 2, B at level 3, C at level 1, and our conflict occurred at level 3, we would backtrack to our highest non-3 level, which would be 2, and undo all the assignments that were made at level 3. So now, let's demonstrate CDCL running on an example. Here, we have a Boolean formula, and we made the guess of not A at level 1, followed by a guess of B at level 2. These two guesses then imply an assignment of C at level 2, which then in turn implies assignments of both D and not D. This conflict at level 2 then gets resolved on clauses 3 and 4 to generate a unit clause not C. Since this is a unit clause, we backtrack to level 0, undoing all our guesses. With our new clause, not C, we have an assignment at level 0 of not C. We then make a guess of not A at level 1, which implies not B at level 1, which in turn applies again D and not D at level 1. We then resolve this conflict on clauses 7 and 8 to generate a new clause A or B or C. This new clause includes two variables at the current level of 1, A and B, so we need to resolve it with another clause used in our conflict, clause 2, to generate our new clause A or C. A is assigned at the current level, so we backtrack based on C to level 0. At level 0, we now have not C assigned, and an implication through clause 10 of not A, which then leads to further implications of not B, D, and not D. Since we have a conflict at level 0, this formula is unsatisfiable. With some extra bookkeeping not covered here, we could actually construct a resolution proof to show clearly and definitively that this formula is unsatisfiable. We'll show one more example of CDCL in action, this time on the same formula that we used DPLL on. So here, we created a guess of not A at level 1, a guess of not B at level 2, and a guess of not C at level 3. The combination of the not A and not C guesses produced a conflict by applying the unit clause rule on clause 2, producing the implication of D, and the unit clause rule on clause 3, producing the implication of not D. This conflict is resolved on clauses 2 and 3 to generate a new clause A or C. Since C was assigned at the current level, we backtrack based on A to level 1. In our updated formula, we create a guess of not A at level 1, which creates the implication of C at level 1. And then those two assignments create implications of D and not D using clauses 4 and 5. We resolve this conflict on 4 and 5 to generate the new clause A or not C. The clause A or not C includes two variables assigned at the current level. Since our learn clause must have only one variable assigned at the current level, we resolve this clause with the clause 9 to generate a new clause, A. This new clause only contains one variable at the current level, A, and is a unit clause, so we backtrack to level 0. With a unit clause in our updated formula, we have an assignment of A at level 0, and then we make a guess of not B at level 1. This produces a conflict, with clause 7 implying not C and clause 1 implying C. We resolve this conflict on 1 and 7 to generate a new clause not A or B. Since B is assigned at the current level, we backtrack based on A to level 0. Now, with our new clause, we follow a series of implications that produces an assignment of A, B, C, and D. We found a complete satisfying assignment at level 0 without having to make any guesses purely by following implications, and we've solved our SAT problem. So we've seen both DPLL and CDCL solve the same SAT problem and compare how they performed. The green clauses presented in the formula are the ones that CDCL learned. We had both algorithms make guesses in alphabetical order, choosing to assign first false and then true. In its decisions tree, we can see that DPLL spent a lot of effort making guesses when A was set to false, none of which paid off. Since this was the first variable guessed on, and DPLL is limited to chronological backtracking, it was stuck making these unproductive guesses until all the possibilities under A were exhausted. The CDCL tree is a little harder to interpret because CDCL does not map cleanly onto a decision tree, but we can still use it to track its progress. After making a series of guesses, not A, not B, not C, we reached a conflict, learned from it, and backtracked to decision level 1. With the learn clause, we immediately reach another conflict, learned a new clause, and backtrack to level 0. Here we make a new guess, not B, which leads to yet another conflict, but after learning a new clause and backtracking, we find a satisfying assignment immediately without needing to guess. Here, even though CDCL started on an unfruitful path of assigning A to be false, it is able to quickly back out of this branch thanks to non-chronological backtracking, and even learns a unit clause A, forcing A to be true after only 2 failures. This demonstrates how CDCL is able to capture information from unsatisfying guesses and use them to its advantage, guiding future searches, rather than proceeding blindly like previous algorithms. Though we've seen CDCL work on 2 examples, we still want to prove its correctness in general. CDCL operates the same as the already proven DPLL except for 2 elements, clause learning and non-chronological backtracking. To show that CDCL is correct, it is sufficient to show that these additions do not disrupt the ability of the algorithm to decide that a formula is satisfiable if a satisfying assignment exists, or decide that a formula is unsatisfiable if a satisfying assignment does not exist. First, let us show that the clauses learned from the conflicts do not interfere with the satisfiability of the original formula. Learn clauses are generated by resolution on clauses that exist in the original formula. By the following lemma, resolution creates a clause equally satisfiable with the original clauses, therefore the learn clause has no effect on the satisfiability of the formula. Lemma. Recall. Formally, resolution is defined as, for some clause A and B and variable x, A or x and B or not x resolves to A or B. If you assume there exists an assignment of variables in A and B that satisfies A or B, then pessimistically, this assignment only satisfies one of either A or x or B or not x. Since x is not included in this assignment, it can be chosen to be true or false as needed to satisfy the clause that has not yet been satisfied. If you were to instead assume that there exists an assignment of variables in A and B that does not satisfy the clause A or B, then there is no assignment of x that can satisfy A or x and B or not x, as choosing an assignment to satisfy one clause must fail to satisfy the other. Thus we've shown the clauses learned through resolution does not affect the satisfiability of the overall Boolean formula. Now for non-chronological backtracking. Backtracking, chronological or non-chronological, has no effect on the satisfiability of the formula or the evaluation of assignments, therefore it cannot lead to wrong answers. However, non-chronological backtracking has no clear and obvious structure, as chronological backtracking does, that intuitively shows progress over the search space. Therefore, it becomes relevant to ask if CDCL terminates, since non-chronological backtracking does not have an obvious progress measure. In order to show termination, we note that through a series of guesses and implications, CDCL either finds a satisfying assignment or a conflict. At a conflict, a clause that was not already present in the formula is generated through resolution and added to the formula. There are a finite number of resolvents that can be produced from an original finite formula, therefore CDCL must eventually produce all possible resolution clauses if it does not find a satisfying assignment earlier. Resolution reduces the number of unique variables in the original 2 clauses by 1 in the resolvent. Therefore, at some point, a trivially satisfiable or trivially unsatisfiable, in this case the empty clause, must be generated from a combination of the full set of original clauses. By the equisatisfiability of resolution proved earlier, this clause would prove or disprove the satisfiability of the original formula, allowing CDCL to terminate after some amount of finite steps. Now that we presented conflict-driven clause learning in detail, let's discuss how good it is at solving SAT problems. So, is CDCL better at solving SAT problems than any other approach? Asymptotically, no. SAT is ultimately NP complete, and that can't be avoided. Though we've seen gains in examples that we've ran, this is dependent on the individual SAT problems being solved. In fact, over randomly generated SAT problems, DPLL performs just as well as CDCL. However, in practice, CDCL has proven effective and makes many problems tractable. In specific, CDCL has made SAT solving practical in applications such as AI planning and software or hardware verification. However, this is not a guarantee that CDCL is always effective. It just so happens that problems from these domains are CDCL friendly. Still, this has proven to be enough of a benefit for CDCL to be implemented in many popular SAT solvers, such as Z3, where they are used in real-world applications. So, if CDCL is NP complete, yet still manages to be an improvement over other SAT solving formulas, where do its savings come from? Well, in both DPLL and CDCL, the benefits of rule propagation are obvious and intuitively worth doing, even if they can't guarantee asymptotic savings. Specific to CDCL, clause learning attempts to extract additional information from failed guesses. More information will not always be helpful, but it can be. This comes at a cost, though. There's additional data to keep track of, and additional logic required to analyze conflicts. It's worth asking, do we want to do this? Often, the answer is yes. For example, learning a single unit clause fixes a variable assignment, and with that fixed assignment, we reduce our total search space by 1/2. Clause learning also helps to smooth out the effect of bad guesses, where we don't get stuck in an unproductive branch, since all failed guesses contribute new information to guide future searches. Non-chronological backtracking is a natural extension of clause learning to jump back to the most relevant decision point after new information has been obtained. This also helps us recover more quickly from descending down a bad guess branch. Unfortunately, that's all the time we have for this presentation, but we want to thank you for sitting through it. We also want to give a special thanks to Fabio Somenzi and Pavel Cerny, whose notes for computer-aided verification helped us in creating this presentation.